locally. It's being recorded in Zoom. Is it resuming? Yes. Okay. Anyways, too bad. I'm just recapping with the final logbook. We have the 3 graphs you were asked to just hand in this morning or last night. Actually, you were only asked to hand in 2 graphs. There's the tables, of course, and then comment on the frequency dependent of those 3 devices under test. Today, we're going to go over the rules of combination. So I expect to see that in the final logbook. I wouldn't expect to see all of it in today's notebook, but logbook, but at least you make a note to yourself. I need to write out the rules of combination. And then we'll have just the 1 resonance plot for the series RLC circuit, and then we could put the 3 devices under test from the past week, the new device under test. And so with combining all these things that we've learned, we can show the plot, and we can show the circuit, and we can explain why the plot looks the way it does by saying, look, this thing is in series with that thing, or this kind of something like that. And again, no report. So you should always put most of your attention on the final logbook anyway, and just use the final logbook. You write a summary of it when you report. Because in the real world, that's the way it works. Up until now, you probably spent all your time just keeping kind of rough notes, and then you report. You did some of the analysis in your report, and everything was in the report. Well, in the real world, all the work is in your logbook, and the report is just summarizing. Okay, so I wanted to get that out of the way, so let's go. The first item on the agenda was to look at the data from last week and check and see everybody make sure that their graphs look like mine. Well, assuming mine are correct, I'm pretty sure. I did find some anomalies, like meaning I have an old spreadsheet that has real data from real components on it. And we looked at the simulation. So, oops, I thought I turned off that ringer. Who wants me? Looks like a robocaller. Let's let that go. I'm using my phone is set up as a camera here, just in case we might get to something over there. Just have it ready to go. So anyways, as I was mentioning before when I was speaking with Felicidad, that the range of frequencies I picked could have been better. You really don't need to have it go up this high, because you see how these things plateau, and with the voltmeters we had and the ability to read our oscilloscopes, it was pretty difficult to get anything other than a 10 here. But if you directly typed in a 10, this thing would complain, right? It would get a divide by 0 because of the way we set this the impedances of each of the individual items, the calculation of it, using V sub VI, V in minus V out. And so that was a problem. And now I understand why how the lab manual has a kind of funky way to do the impedance, but I think it avoids the divide by 0 problem. So at the end of the day, this is the graph that matters. This is now the log-log plot. And the interesting thing is that in the real world, with real items, so let's see what we have here. I have now, this is data plot. Up here. this is the theoretical prediction, just using the formulas. And then I have here an overlay, and it's sort of a work in progress because I have it set up where I can type in fit values to try to make the theoretical lines lay on top of the real data. And one of the things that I have here is that I have added a constant term to the inductor. So, and why is that? Well, an inductor, so let's get this guy here and make that bigger so you can see it. So when it says the X or the chi there, that means it's the theoretical prediction. So an ideal, remember an ideal capacitor, you might remember, so an ideal capacitor has a resistance equal to infinity. And that's the real part, the DC part. And an ideal inductor, we didn't go into how an inductor is made. An inductor is really literally just a coil of wire. So an ideal inductor has an R equal to 0. Well, it's impossible to create something. It's easy to create something with an infinite resistance because that's just a capacitor is kind of the definition. If I have a wire and I break it, then this becomes R equals infinity. No current can flow, right? I equals V over R. R is infinity, no current. Well, that's easy to create. But R equals 0 is impossible. And so, in general, when you see an inductor inside of something, and I'll have to get some examples, but I have something that looks like one. Inside, if you look at inductors, they tend to be big things, and they use very heavy copper wire so as to minimize the resistance. So that's why if you look at the data up here, so if it's expressed as a Z, that means it's something I measured. I'm increasing the font so you guys can see it better. So the resistor is just a flat line, and the resistance of an inductor goes down if you go down in frequency, but notice how it becomes flat here. That's because the real inductor does not have a 0 resistance. In this case, I've set the theoretical inductor to have 0 resistance here, but I added the possibility of adding its own resistance. And now you see that it curves at lower frequencies, just similarly to a real one. But even so, you notice that the capacitor and the inductor, the real ones, tend to be straight lines in the log-log plot. And it's an interesting feature of these things that the slope then of an inductor is +1 and the slope of a capacitor is -1. It's always true. And I'll show you that next week just as a point of interest. Just like last week when we went over final thoughts on the cardiovascular lab, lab. We'll do that next week, but you won't be responsible for that material, just to fill in all the corners for the people who are interested. And so But so even real data, well, it's a little funky down here. So if I look at our data, well, maybe it's, we don't have the luxury of error bars. I was still kind of surprised by this. In general, you expect the curvy line. Oops, wrong button. So if this one here, right, so if I take this and make this linear, see, that's when I expect it to look curvy. Same thing here. And this is also why it's important to use, it's another good reason here for using logarithm. See, I expect this to look curvy, right? So I don't see anything wrong with the, see, the capacitor and the inductor look the same. But when I move it to log, then I see all of a sudden, uh-oh, look at that. The two behave differently. So in our data case, this is the log. And there's, so that, oh, here it is here. So I have all three of them. So this was a little surprising. And, I can't complain. Tinkercad is, at the end of the day, pretty awesome. And the reason it gets funky up here and down here is simply because I shouldn't have given you such high frequencies to go with. But anyways, hopefully, well, I'm recording this, and you've been writing notes to yourself about this. These are all things. Oh yeah, why can you say? Why should the log plot be a straight line? I'll give you a little bit. Oh, you don't have to do this. Let me show you why. Here it is. Oops. Okay, it's all one. So I have my equations for the impedance of each one of these devices under test. If I take the logarithm of both sides, which is just kind of what you do when you do a log plot, watch what happens here. So I've got, say, log of ZL, and now we want to think in terms of a straight line fit, right? So I look at the inductor equation, and oh, there's frequency. So it's log F, and then let's see, nothing else has a frequency dependent. So in fact, these are constants, right? So this is the y-intercept, and the slope here is 1. It's implied. You don't usually write the 1 out, and it's +1. And that's a surprising result. It was to me the first time I did this. So you expect the inductor to have a slope of 1. Now, and then the way you determine what is by a fit, like I'm not asking you guys to do this, but the way you determine L from the fit is to find out what the y-intercept is. Isn't that a trip? That's like one of the few times that when you do a fit that you care about the y-intercept, at least the y-intercept being your primary source of information. And then if you look at the capacitor, log Z of the capacitor, that's equaling to minus log of F. So that's a -1. And the y-intercept is minus log of 2 pi, which is a constant, minus log of C, which is also a constant in this graph because you're using the same capacitor every time. And and earlier the same inductor. And this is why you do the log-log plot, so then you can. It's just something that I can't tell you ahead of time that it's natural to take the log-log plot. It's just people play with these things and they say, oh, wow, if I take the log of both sides, if I make a log-log plot, I can do this straight line fit. And next week, too, I'll do some demo of I can put on the oscilloscope screen the behaviors of these things. We've seen, I think I've shown you the time constant of a capacitor. And the time constant of an inductor is the opposite, actually. And they do, what are they, like, a capacitor sort of preserves, no, I can remember. There's like hand waving description about one resists change and one helps change. I don't remember anymore. I tend being I have a degree in physics, so to me everything is math when it comes to these things. Okay, so I think and right, so you need to jazz these up. This could have a bigger font, for example. It needs axis labels. Axis title, excuse me. So there's the vertical one, etc., etc. Any questions on this stuff here? This stuff that from last week? Okay, so you're gonna, try and fill out the table. As I said, you can probably, let's say, just go up to 40,000. If you haven't finished it yet, and it was giving you problems, just go up to 40,000, because what happens is that we don't have the ability to twiddle knobs on an oscilloscope screen, and so it's very difficult to measure it once it gets, tiny differences. It's difficult to measure when you're using the Tinkercad oscilloscope, as somebody who was texting me this morning noticed. Yeah, the real one. Yeah. Oh, well, you know what? I can show that to you. Let's think about this. What do I have here? How? Let me finish. Felicia Dodd. Let's plow ahead. Let me get all this other background I'd like you to have, and if I don't get to it this week, I'll do it next week, and I'll show. I can make this very same table with real components. How's that? Okay, good. And then, oh, that's great. Then we can look at great, great. So we have basically an agenda for next week, and if on the week 15 we'll just play with some geometric optics, right? So next week will be like all kinds of concept stuff that you won't be responsible for, and because I got all this equipment over here because of my basic electronics class, and I also have the on-screen, the USB-based oscilloscope down there, and then all the other toys I've got here. So we can certainly do something impressive. And right, no, where is that? Well, we don't need this. I was going to zoom this out. And I get so ADHD sometimes. I see something that needs to be done, and I can't help myself. Oh boy. Okay. So